Yeah. Okay, so let me introduce the speaker. So hello, everyone. Welcome to this session of ASI seminar. Today we'll have Jason coming here to tell us about the Helion languages. So maybe a bit background about Jason. He's a research scientist at Meta and a big technical lead for PyTorch compilers. He started the Torch Dynamo and Torch Inductor projects, building flexible graph capture and high performance compiler to PyTorch 2. Yeah, he got his PhD at MIT and had 15 years of experience in ML, compilers, and programming languages. And with that, Jason, please take it away.
Wonderful. Thank you for having me. I'm delighted to be here. So today I'm going to talk about Helion, which is a new language for machine learning kernels that we've been developing over the past few months. So to start off, let's start with a motivation, sort of like why do we need a new DSL? And a lot of motivation for a DSL is there's thousands of custom kernels in use at large companies. And especially when custom kernels are written in really low-level languages that are specialized for hardware, they turn into tech debt pretty quickly because a custom kernel is like super fast for the current generation of hardware, and then a new generation of hardware comes out, and sort of all those optimizations for the previous generation now just make it more complicated and harder to port it to the new generation. So we really want higher level abstractions for writing custom kernels. And the way I like to think about it is sort of this part on the right side of the screen, where you have many different hardware languages for writing custom kernels at different abstraction levels. So at the very lowest level, you have PTX, which is allows you nearly complete control, but it's very hard to write. It's very hardware specific, so it's not very portable. While sort of at the highest level of abstraction, you have PyTorch. And Helion, sort of as a level of abstraction, fits sort of between PyTorch and Triton. So in Helion, you can have a lot more control over exactly what gets fused with what. You can have a lot more control over tweaking algorithm implementations if you want to sort of iterate on new things. But compared to PyTorch, but then at the same time, it's higher level than Triton. So a lot of the things that are sort of very manual in Triton, like tensor indexing, grids, defining search space, argument management, templating, all those things are more automated in Helion, which allows you to sort of hopefully write less code, but sort of more meaningful code where you're really just writing sort of the meat of the algorithm, and then letting the autotuner sort of search over good implementations. And one of the really big things that sets Helion apart is autotuning. And so one Helion kernel maps to many different Triton kernels. So for every Helion kernel, you have the kernel and then the configuration. And given the configuration, Helion gets lowered to Triton. The configurations here are much wider and than the configs that you might have for Triton, and they actually map to completely different Triton kernels. And so the auto-tuning process is you have this search space and the other big difference in Triton is that the search space is created implicitly. So in Triton, the user has to explicitly list every single config that's going to be tried, and it's sort of hard to come up with okay, what configs are good to try. Any choices in that search space need to be defined manually. And with Helion, it's all implicit. So basically, if you write an HL.tile construct, that implicitly defines some search space over block sizes, iteration orders, etc. And so the Autotuner will search thousands of configurations, and the idea is that this auto-tuning process happens ahead of time. So we don't think users should be auto-tuning every single time they run their model. What they should do is they should as they're developing the kernel or whenever they're porting the kernel to new hardware, they should run the auto-tuner and they should basically check the configuration into their code. So you get very fast compile times. It's very repeatable. It's deterministic what config you get. But this allows sort of the process of onboarding new hardware is basically just re-auto-tuning all your kernels. So here's an example of a matrix multiply in Helion. And the Helion kernel has two main parts. So there's this outer part, which we call the host code. And this code is just standard PyTorch code. And so what you do in this code is you allocate, you compute sizes, you allocate output tensors, and so on. This is basically combined into the kernel, so you don't need to write a bunch of boilerplate to pass in all the stuff you computed in the host wrapper into the body of the kernel. And then you have this other part of the kernel, which is basically everything inside the hl.tile loop. And this gets mapped to device code. So this is going to get compiled down to Helion, compiled down by Helion into a Triton kernel. And the outer loop here, this tile n loop, basically becomes the grid of the kernel, if you're familiar with Triton or CUDA. And then hl.tile loops inside the body get turned into loops within the kernel. And within this body, basically, you're operating on tiles of elements, similar. So it's a tiled programming language similar to Triton. And you're basically defining, using PyTorch operations, what should happen on every tile that you process. And so sort of the core language constructs is this hl.tile loop. And hl.tile basically subdivides a multi-dimensional iteration space into tiles. And the exact details of how it gets subdivided are auto-tuned over. So the tile sizes, the iteration order, swizzling for cache reuse, loop flattening, all of those are or whether you're doing one-dimensional or two-dimensional or however many dimensional you want iteration, all gets auto-tuned. And this sort of it captures the semantics of hey, I want to tile my program, but doesn't ask the user to tell you exactly how it should be tiled. Within the body of the loop, standard PyTorch operations can be used. So that means that if you're familiar with PyTorch, you already know most of the Helion language, which will hopefully make it easier for users to onboard. And we reuse Torch Inductor, which is a part of Torch Compile, to load these PyTorch operations into output Triton code. And Helion supports control flow at the top level, and a function which it's useful for a lot of cases. So I showed an example of a for loop, but you also can do if statements and so on. So another cool feature of Helion is templating via closures. And often what we see in custom kernels in the wild is a lot of really small variants of the same kernel. Like you might have like a mapmul plus a relu kernel. You might have a mapmul plus a bias plus a relu kernel, Helion allows you to basically pass in a Python function as an argument to your kernel, and you can call this. And you can do the same thing in Triton, but the big difference in Helion is that we support capturing variables inside of closures. And so here in this example, I have this bias tensor, which is allocated in global scope. And then when I pass in a function here like a lambda function, that lambda function can use the bias. And that bias is going to get implicitly lifted into an argument to the kernel. And this supporting closures this way actually makes these lambda functions much more powerful because you can have epilogues here that require new input data. And you don't need to sort of do the work of threading these sort of extra inputs that are needed by functions as arguments to both the wrapper code and then also the kernel itself. And this single change sort of allows things like flex attention, which is implemented in PyTorch using Jinja templates, which is actually codegen source code, to be implemented just natively in Helion. And so this is a pretty simple thing because we're reusing Python language constructs, but it makes it much easier to reuse and sort of do templating type things in Helion. So how is the Autotuner used? Today, this might change in the future. The Autotuner takes about 10 minutes to search 1,500 candidate Triton kernels. Right now, we're mainly using differential evolution, but in the future, we're interested in other types of search techniques, such as using like LLMs or reinforcement learning or shared performance databases. And I think there's a lot of room, and we're definitely open to contributions from the community as well in like how do you search this configuration space more efficiently? And especially as Helion and as the kernels written in Helion get more complicated, the search space, the size of the search space will grow, and using efficient auto tuning techniques is going to be increasingly important. And so at the end of auto tuning, Helion prints out this message, and I'm giving an example of it here. And basically, what it's asking the user to do is to copy the configuration found by the Autotuner into their source code. And so this is an example of it. So you can see in this example, we have the same map model as before, but now you basically have passed in the config equals to helion.kernel. And at this point, now it'll just skip auto tuning. So you've now basically hard coded this configuration, and it'll sort of act sort of functionally just like a Triton kernel, where there's no sort of runtime auto tuning required. You can also pass in a list of configurations, and it'll do sort of the more constrained finite search the same that Triton does by default. So here's a bigger example. This is an example of an attention kernel written in Helion. I'm not going to go over the details of the attention kernel. This is checked into the repo if you want to take a look. But I think it illustrates sort of the different levels of abstraction that you have here. So in attention can obviously be implemented in one line in PyTorch. You call just scale.product attention. It takes about 30 lines in Helion. 120 lines in Triton, and I looked at like the Kotlin implementation of mapmol, and it was like tens of thousands of lines. It was really hard to count, but it's definitely more than 1,000, and so it gets much bigger. So this gives you an idea of like, okay, here's different levels of abstraction, and I think it's important for users to pick the level of abstraction that's right for them, and sort of it gives them the level of control that they need. And an important thing to note is that the local level languages, including Triton here, actually specialize in some interesting ways. So both the Triton and CUDA versions actually hard code assumptions about tensor layouts. So if you pass in like transpose, if you take one of the inputs to the attention and you transpose it, both the Triton and CUDA versions are actually silently incorrect, and they'll just do the wrong thing. And the CUDA version actually also hard codes a lot of assumptions about the hardware, where you actually have different versions for V100, H100, B200. So here's some performance data for attention. So here I have a CUDA version of attention, which is the one basically just calling torch scale.product attention, which under the hood uses flash attention 2. I then have 3 different Triton attentions. So I have the non-TMA Triton attention from the Triton repo, the TMA version of it also from the Triton repo, then Flex attention, which is a template-driven one, template-driven version built into PyTorch, and then the Helion version of itself. And here I'm showing speedups over a naive implementation of attention in PyTorch. And if you compare the Helion version to the Triton versions, you can see that in almost every case, Helion is faster than the Triton versions. And the reason for this is it has a bigger search space. So it's obviously, because Helion's outputting Triton, it's obviously possible to get sort of the same performance as Triton, or as Helion using in Triton. But because Helion is searching over a longer set of configurations, especially on the smaller sizes, you can see it racking up much bigger wins, because basically the handwritten Triton versions have basically overfit for certain sizes, and Helion's able to find configurations that are better for these small sizes. And then looking at the flash attention 2 numbers, you can see that flash attention 2 is faster on the smallest size, and then slower on the others. Which is an important thing to know, that just because something written in CUDA doesn't necessarily mean it's going to be faster. It requires sort of a lot of human work to actually squeeze performance out of it. And so I think I don't have the flash attention 3 numbers here, but I think flash attention 3 actually is faster than all these. But that's sort of the result of sort of heroic human effort to hand optimize these kernels, while the Helion version is basically just a naive attention algorithm that's been auto-tuned. So sort of the level of effort comparison between the two is pretty striking. So here's a bunch more speed up numbers. These are for a variety of norms and also a jagged kernel and an embedding. This is speed up or PyTorch eager. So PyTorch eager is 1x, and anything bigger than 1, bigger is better, and anything bigger than 1 means that it's faster than PyTorch eager. And comparing Helion to handwritten Triton. I think most of these handwritten Tritons are taken from Liger, which is a somewhat widely used kernel library of handwritten Triton kernels. So they're hopefully realistic. And for each of these numbers, we're running many different shapes, and we're averaging the performance across all the shapes. And you can see here that across the board, Helion is faster than the handwritten Triton. Again, because it has a larger search space and is able to find better configurations for each config. You can see there's a very big speed up for the jagged version. This is because PyTorch doesn't have native support for jagged, so the baseline is just a lot worse. And so this I think is really a big testament to autotuning tuning works, and it allows you to squeeze a lot more performance out by searching over the right sizes, or the right configurations rather. Okay. So next I want to talk about the configuration space, and I think the configuration space is like a really great way to sort of understand what Helion is doing. Because basically I'm going to show sort of the configurations and sort of how that affects the output code that Helion generates. So the first type of choice I'm going to talk about is tensor indexing, and this is an area where Helion is a lot simpler than Triton. So Triton actually has 3 different ways of doing indexing. You can do pointer indexing, where you're basically doing index offset calculations using tensors of pointers. It has a block pointer mode, which is used by a bunch of accelerators for Triton. And it also has tensor descriptors, which are mapping to hardware in Blackwell and Hopper. Helion just has one type of indexing. Helion indexing, you just use sort of PyTorch style indexing, where you pass in tiles rather than explicit indices to basically load a tile of elements. So you can see here that this sort of very simple load from X in Helion is, depending on the value of config.indexing, is mapped to one of the 3 different indexing styles in Triton. And we've actually found that it's not always clear which one of these is faster. So sometimes tensor descriptor is faster, sometimes pointers are faster. And manually in Triton, the lot of work to rewrite your program to switch between these different modes. And Helion allows sort of auto tuning between these different ways of writing your program very, very easily. The next big piece of the search space is block sizes. And so I mentioned block sizes a bit earlier, but basically if you have a loop here like hl.tile over x and y, this is implicitly creating these block size 0 and block size 1 variables. And these block sizes need to get sort of threaded through the code. So sort of like at the bottom here, you can see that the kernel is getting called, and you need to compute the grid size based on the block sizes. Then you need to pass the block sizes into the kernel, and then within the kernel, you need to use the block size in a lot of ways. And so by making this block size definition implicit, you save all this boilerplate of sort of threading the block sizes through your program, and it is sort of all automatic. And you basically specify the block sizes with this block sizes parameter, where basically you pass in just the sizes that you want. And this also allows Helion to do other optimizations, such as loop flattening. So if I take the same kernel that I had before, and I pass in flattened loops true, then what that actually does is it takes that 2-dimensional block size, and it turns it into a 1-dimensional block size. So we basically collapse the 32 by 32 block into a flat 1024 block. This sort of transformation results in a lot of changes to the output code, because now you have just a single block size that you still need to thread through your program and then do different math based on it. And this is just a single Boolean change in the Helion configuration. So the next optimization I'm going to talk about, or configuration, is reduction rolling. If you write something like load an entire row of a tensor and then sum it up in Helion, this ends up mapping just to a TL.sum. The one subtlety here is that the block size you load needs to be rounded up to a power of 2, because Triton requires power of 2 blocks. Helion does this sort of rounding up for you automatically. So when you put in this colon here to basically load the entire row, it's sort of implicitly rounding up to the next power of 2 for you. But this sort of simple way of writing a reduction in Triton has a problem that if your row size is very large and doesn't fit in registers in a single SM, this kernel will actually this first version of the kernel will actually just entirely fail to run. And even if it doesn't fail to run for like very large row sizes, it can get this version can get slow basically because it has a lot of register pressure and forces registers to spill. And so there's a different way of writing a reduction. We actually turn a reduction into a loop where you have sort of an accumulator here, and you basically loop over all your data, sort of summing things up in the accumulator, and then you do the sum and add. So we call this sort of a rolled reduction or a reduction loop. And switching between these two types of doing reductions is also just a configuration change in Helion. This reduction rolling algorithm works even if you have data dependencies between multiple reductions. So if you have like a softmax operation which needs to take 2 or 3 passes over your data, you'll actually it'll end up generating multiple of these loops and recomputing anything that needs to be recomputed in order to do this rolling properly. So the next configuration I'm going to talk about is the PID types. And so PID stands for program ID. There's actually a number of different ways of writing your program. And there's 4 of them that Helion's able to generate. So if you have a flat PID type, then you just sort of then you basically are only using the X dimension of the launch grid. And you're just computing here the number of programs that need to be launched. XYZ programs will use the multiple things. So this is probably the most naive way of writing it. This might be how a lot of the examples will look like. But then you have these 2 types of persistent PIDs. And for persistent kernels, instead of using the launch grid, you just launch the number of SMs programs. So both of these just say launch the kernel with num SMs. Then within the kernel, you end up having a loop. And that loop is going to loop over the sort of virtual PIDs. That's going to loop over the virtual PIDs. Is sometimes more efficient. And so you're able to, just by flipping a configuration, search sort of over all of these, which could result in some sort of moderate rewriting and can be difficult to search over manually. So another optimization is L2 grouping and loop reordering. So comparing sort of the top left to the bottom, you can see that you can change loop orders. So you can swap loop orders, and the swapping loop orders works for both for PIDs and also for loops in the body of the program, which basically changes iteration orders, and depending on how your data is laid out, different iteration orders can be better. And then there's also an L2 grouping optimization. So this basically does some blocking in 2 dimensions to try to increase reuse for matmul algorithms and basically have better cache efficiency. And so these types of PID reordering optimizations are automated and auto-tuned over. And then sort of the last sort of class of things are just Triton tunable. So these config values basically get passed 1-to-1 down to Triton, and these are basically knobs which Triton exposes, which Helion auto-tunes over. And then the big advantage that Helion gives here is just they're automatically explored. Like a lot of users don't even know that these flags exist. They might not know how to set them. And by auto-tuning over them, we can explore these automatically. And then the last thing I'll talk about isn't actually a configuration. So the autotuner isn't actually auto-tuning over this because this is needed for correctness, but it's automatic masking. So like one gotcha when writing a Triton program is if you write codes like this, where if you take like x plus 1 and then you sum it up, well, because Triton requires power of 2 blocks, for the last elements of a block might not actually exist. So they might be masked off because your block is size 64, but you only have 60 elements. So you have these sort of last 4 elements that are just 0 when you load them in. And if you add 1 to a block and then sum it up, those sort of masked off elements, which should be 0, end up getting 1 added to them and become 1s. And this is sort of like a foot gun in Triton because it can be really hard to get this correct. People forget to do it. And if you're only testing your program with power of 2 inputs, then this isn't really a problem. And so Helion has an analysis in it to basically automatically do this masking. So here, you can see the output code where we've inserted a mask before the sum to have this correctness constraint, where basically Helion is sort of tracking which elements of a block are real elements versus which ones should be masked out, and basically before any operation, which is a reduction operation, it's ensuring that the proper masking is inserted. And there's optimizations here. So if I set static shapes equal true and I have divisible sizes, so if I'm passing in a power of 2 input, Helion will optimize away this masking for you. So next I want to talk about the internals of Helion. I won't go into too much detail here, but basically the way it works is this is sort of how the flow of the internals of the Helion compiler works. So we start off with the Python AST. Helion processes the AST using AST parsing. We first do a type propagation pass. This type propagation pass adds type information to every node of the AST, and also a bunch of other metadata. We then convert this extended AST, which has the types and metadata, into what we call device IR. This device IR is an FX graph or a collection of FX graphs where you have one FX graph per basic block. It's in an SSA form. It has control flow and phi nodes that sort of connect multiple graphs together. Every node in this graph has a pointer to an inductor IR, and so this inductor IR is used to do cogen on it. We have a number of compiler passes which basically do transformations on this IR. Sort of an example of a compiler pass is the reduction rolling, which I mentioned before. And then sort of after we've done a bunch of the compiler passes, we do cogen, and cogen is the point where I have a config. So basically everything to the left of this diagram just runs once per configuration. So if you're auto tuning, you don't need to repeat sort of the left half. And then sort of the config comes in at cogen time, and we generate the output Triton code using the Python AST module. We also, for the wrapper code, for the sort of the host code, which is just standard PyTorch, we do AST rewriting to generate sort of that wrapper code, or we basically replace sort of the HL.tile loop with a call to the generated Triton program. So current and future work, what are Helion's still super early. We're actively developing Helion. And so here's just a few of the things that we're either working on or think we need to do. So we want new language features. I've talked a little bit about new auto-tuning approaches before, basically applying more ML-driven approaches to do the search. I think we need better caching for the auto-tuner. So in some cases, you may not want to copy and paste configs into your code. You may want sort of a caching service that handles the auto-tune configs. We're looking into new hardware backends, AMD, and then also a bunch of others. We're looking at mixed communication compute kernels, improving performance. There's some cases where there's performance gaps, and in those cases we want to we're working with trading teams to basically try to expose more knobs and tweak the code we generate to squeeze out more performance. And then as we get closer to our beta release, we're going to write more docs, more tutorials, and hopefully get some user testing to get sort of early feedback to harden the language. And so this is my last slide. I want to thank you again. I'll throw out a sort of an early development warning, which is on our GitHub. But if you're trying this out, you should be aware that we're still sort of an experimental phase from the project. So you should expect bugs, incomplete features, and we might change things that'll break kernels, and so be forewarned of that. That being said, like I think the current language should be very usable, and we'd love for you to try it out and tell us what you think. Sort of this is sort of an exciting sort of early time in the project, where the feedback from you and from the community can really help shape the language and help make it better. So we'd love that, and we're definitely open to open source contributions as well. And I'll have a link to the code and the documentation. Yeah, thank you so much.
All right, thanks Jason for the very nice talk. I see a couple questions in the chat, so maybe I can just summarize the question and then just you can answer them.
Okay.
So the first question someone asked is Helion going to be the backend for Torch compile?
So we're thinking about using Helion for the back, basically as a replacement for templates in Torch compile. So Torch compile contains right now a bunch of Jinja templates where we're generating Triton source code basically by doing like string replacements. And I think Helion would be like a really good fit to basically replace those handwritten templates. For using Helion for regular for like torch inductor sort of mainline code gen, there's sort of this circular dependency problem because Helion actually uses torch inductor to generate Triton, and so there's like some technical challenges to having, because if Helion if a torch inductor generates Helion and then Helion calls into torch inductor to generate Triton, it sort of becomes circular. I think there are some like technical ways you can address that. But the other challenge is just auto tuning is very expensive, and so for like a single kernel, you can afford to spend 10 minutes auto tuning. But if torch inductor generates like 200 kernels, you can't really afford to spend 10 minutes auto tuning every single one of those kernels, and so there's a lot of challenges there. So I think sort of in the short term, probably only for sort of the templates that are in torch inductor. But longer term, who knows? we'll see.
So the next question from Zika asking, when auto-tuning, does the shape of the input tensor matter for what kernel is the best? How does the auto-tune manage if this is not specified in the code?
Yes, so when you auto-tune, you need to specify an example input to auto-tune on. And so if you're using a kernel in a situation where you have like some wildly different inputs that you're passing to your kernel, it would make sense to auto-tune each of those sort of classes of inputs separately. And the current version has some bucketing where depending on if you set static shapes equals true, then every single unique shape will sort of get bucketed into a different bin. Otherwise, we bucket based on sort of more coarse-grained metadata. But because sort of Helion exposes these configs to the user, right now we're basically relying on users to sort of manage that configuration. When I was sort of talking about future work, sort of that like auto tuning cache I was talking about is maybe like a more more sophisticated way of handling that, where like you can imagine you having like a caching layer above Helion, which does some sort of categorization of the sizes and sort of depicts which config to use based on the sizes, based on sort of like a pre-computed database. That doesn't exist yet. Like right now, we're basically saying, okay, the user tells us what config to use. the user ran the autotuner themselves and sort of is like thinking about these sizes. But it's definitely an area of improvement, and it's one where I'm not sure like there's a one size fits all solution. Just because like in some scenarios, people really care about predictability and reliability, and they don't want like having like a surprise auto tuning is like totally not acceptable. But we'd I think having some sort of like good defaults that people can use to create that sort of caching layer is pretty important for usability.
Great. I see Braden raise your hand, but please just unmute yourself and ask a question. Okay, so I'll keep going through the question. Wait, let me okay. So the next question from I believe from Ad is I think one of the slide you mentioned is that TMA is faster than the non-TMA version. Could you say a bit more about this?
Yeah, so I think I mentioned the other way around. Like for the example that we tried, TMA was actually slower, and that's not true always. Basically, like what it is sometimes TMA is faster, or sometimes TMA is slower, which is why it makes sense to have an auto tuner to try both and pick whichever one's fastest. And the sort of under the hood, TMA is mapping to different hardware. So sort of in NVIDIA, there's like one set of hardware instructions for a TMA load. There's a different set of hardware instructions for like a coalesced load. And there's depending on how something gets used, one could be better than the other, because if you sort of load into the wrong part of memory, you might have to have a copy after the load. But sort of empirically, what we found is that for if you have like a standard map model, TMAs are usually better. But if you have sort of like a more complex kernel that's not sort of primarily a map model, it's sort of more of a toss-up, and it's not really clear which one's better.
Interesting. So I think the last two questions, and I have a couple more actually for myself, actually a little bit more. So maybe some of the two last questions are relevant. One question from Wentao is, so Helion can call PyTorch functions in the kernel, but how many functions are from the PyTorch say are allowed in the Helion kernel? And then the follow-up question from Don is, how will Helion be adapted into the PyTorch under your plan?
So I'll answer the first one first one and then circle back. So most PyTorch operations are supported. So and since we're relying on torch inductor, basically the support of torch inductor is very related to the support of Helion. So portwise operations are generally supported. Reduction operations are generally supported. View operations and mapmall operations basically get mapped to sort of their corresponding things in Triton. And sort of those cover the vast majority of PyTorch operations. PyTorch has a lot of long tail things in it, where there's like PyTorch has like an FFT in it. FFT isn't supported. PyTorch has like LU factorization, like all these sort of like linear algebra functions, but I'd say like if you pick sort of a random PyTorch operation, it's probably supported by Helion.
And then, so actually, I have some questions on my side. So one question I've been thinking a lot about is this sort of how do you come to the sort of the design of Helion? Like basically, Torch compile had this like automating, right? The PyTorch function you lower to the Triton code, whereas trying to have very lot of or even something called like Colors, you have a much more fine grained like or Gluon, they have much more fine grained control. So how do you design a Helion? How do you pick out like how do you decide what is the abstraction for Helion that you want to use it to write the kernel for?
Yeah, that's a good question. Definitely like I'm sort of coming into this with my own sort of perspective, and likely like a lot of it is sort of like the perspective that I'm coming into with it. And so like I sort of built Torch Inductor. I've been working on Torch Inductor along with a wonderful team helping me. And the process of working on Torch Inductor it involved generating a lot of Triton code. And so I've written a lot of Triton kernels. I've written a lot of compiler type things which generate Triton kernels. And so, from using Triton, there's lots of things that are just sort of tedious in Triton. Like, indexing calculations are really tedious in Triton. Having to keep track of pointer math, having to rewrite your program to use TMAs. That's something that's like, there's clearly like, that's too low level in a lot of cases. There's also things like boilerplate, like having to compute the grid size. Like it's really easy to get the grid size computation wrong, and basically like every single grid size is just the number of elements divided by the block size rounded up. And so it's like tracking grid sizes is really annoying in Triton. Similarly, like argument passing, like if I want to fuse an epilogue onto a Triton kernel, well, I need to like add all the new tensors that are needed by the epilogue to the arguments of the kernel. I need to add all the sizes to the kernel. Like managing all these arguments was sort of like a huge headache. And so there's sort of like these areas that through experience with Triton, I'm like, this is hard to use. Like it would be way better if we had like a higher level of abstraction that sort of automated a lot of that stuff away.
Yeah.
And sort of coming from the other side, I'm also a PyTorch developer. I work a lot on building PyTorch, and often sort of like working with our users and working with users of Torch Compile. Torch Compile wasn't designed for and doesn't provide users low-level control. Like a lot of users say, like I want X to be fused with Y, and sometimes Torch Compile will fuse X with Y automatically. Definitely, as I hope it does, but if it doesn't, the user's sort of out of luck. There's no way to like force Torch Inductor to like fuse specific things together. There's no way to like have sort of like fine-grained control over that. And that's something that a lot of users ask for. They want to actually be able to control exactly what goes into the kernel. And give that control. And so sort of like from that spirit, I'm like, okay, there's this gap in sort of the language space between Triton and PyTorch. Like, PyTorch doesn't give users enough control. Triton has like too much boilerplate that's like hard to write. And at the same time, I'm a huge believer in autotuning. Like if you go look up my PhD thesis, you'll see autotuning in the title of it. So I clearly have like a long history of autotuning. And so I really believe that like the best way to get performance, especially across heterogeneous hardware, because increasingly, I know sort of at a lot of different companies, we're seeing many different types of devices being deployed. And so like, how do you get portable performance? How do you get performance that doesn't sort of get stale as soon as a new generation of hardware comes out? Is really use autotuning. And so there's sort of like those pieces sort of together, sort of like pointed to sort of like a whole in sort of the abstraction space. And so sort of that's sort of like what motivated the design. And hopefully Helion sort of fills that hole that I envisioned. Hopefully other people sort of agree with me that yes, there's like sort of a hole in that abstraction space. If it is, then it'll be a successful language. I also sort of think that I don't think Helion is the one language to replace them all. Like I think there's still a place for CUDA, right? Like there are times when you want to go much lower level than Triton. Helion isn't sort of the solution. If you want something lower level than Triton, then like Helion is clearly higher level than Triton. It's sort of going the wrong direction. But hopefully there's sort of an audience that wants a bit more control than PyTorch can give you, but something that's a little easier to use than Triton.
So actually, maybe a related question to sort of the front end of the language, also the back end. which is like when you design the backend, it's like very tied. I mean, the front end design definitely tied to the backend compiler and also the sort of the intermediate representation. I'm curious, what's your sort of your meta process of coming to the specific choice of device IR, and how do you think about sort of the designing the backend? Like, do you come to you think about the right abstraction, design that device IR, and then write the compilers, or you think about what makes sense from the compiler point of view, and then design the IR, and then design the languages to support this?
Yeah, I do spend a lot of time thinking about it. I sort of like love my job. I enjoy working on this. I enjoy sort of thinking about this stuff. So like often sort of like, when I'm off, at the gym, I'm thinking about like what's the right abstraction for this. But it's also like I don't think it's the case that it's like it's an iterative process. It's something that, like my very first ideas for Helion has sort of evolved over time. I implemented them, I prototyped them, and sort of like as I try to like implement certain optimizations, there's been not that many, but there have definitely been cases where I'm like, oh, I got that abstraction wrong, and so I go and like, luckily it's still early enough in the project that I can go and change things and iterate. So I think like it's something that I think there's like a piece of experience of it. Like I've been working in compilers a long time. There's a piece of iteration, of just sort of trying stuff out and getting sort of signal through experimentation, and being sort of not afraid to try different things, and then also just like thinking hard about this and working on it.
Okay, so the TLDR is go to the gym and then think about abstraction design. That's the TLDR.
Yeah,
I think
maybe.
there are a couple more questions from Mitt. Mitt asks, is Prolog supported? And then is there a way to automatically generate the backward kernels?
I'm not sure what he means by prologue. Um,
Mitt reply fusion.
Oh, Prolog Fusion. So currently, the way Helion is done today, there's no automatic fusion. So basically, the Helion kernel you write is the Helion kernel you get. One thing we're planning to do in the near future, but is not implemented yet. This is something that I'm expecting to come soon. Is automated fusions with inductor, where if you torch compile a Helion kernel, at least in theory, you could take PyTorch operations, which Torch Inductor is compiling, and because they use the same IR, because they both are using Torch Inductor IR, it should be possible to basically fuse external operations into Helion kernels, either as an epilogue or as a prologue. But that is future work and not yet implemented. And so hopefully we'll have that soon. And then in terms of backwards, another thing you could do is, because Helion consists of PyTorch operations, we actually have this is mostly finished in the code base, but not there's still some rough edges in it. Is we have a reference mode where basically, like conceptually, if you look at that HL.tile construct, well, if you just set the tile size to be the entire tensor, then you have like a coherent PyTorch program, right? If HL.tile just returns like a full slice of the tensor, then you'll just process a single tile. It'll be mostly PyTorch operations, and you'll basically get a PyTorch program. That's good for baselines, because we can like run against either PyTorch automatically. We can run against Torch compile automatically. But the other thing that we could do is we could use the AutoGrad engine to compute the backwards of that kernel. And so we could actually generate a backwards of a Helion kernel automatically. That backwards would be just PyTorch operations. So it wouldn't be a Helion kernel. It would be like something you could torch compile. That'll be like convenient in the case that you call a Helion program during the forwards of your training, and we can compute the derivative of it for the backwards, and then compile that with torch compile. So that's something that we want to do, but it's also not yet implemented. So that's this sort of an aspiration that hopefully will be ready soon.
Yeah. Actually, I like this idea a lot. Actually, I really like this idea of having the reference partition implementation, which derives the autograph, and then have the backward kernel, which is like whenever I write on kernels, the thing that struggle the most is the backward implementation, which I think this is actually a very clever idea.
Yeah,
Uh,
yeah.
so one question from Zuck asks, is it a hope of Helion discover things like flash attention, or really generally, does it support algorithmic rewrite at all? Because for now, all the auto tuning are happening on quote unquote the scheduling. But do you think algorithm rewrite will be part of the Helion in the future?
So right now we're not doing any major algorithmic rewrites. I mean, you could argue that like the loop rolling stuff is like a minor algorithmic rewrite, but things like turning like bubble sort into quick sort uh, or like a naive attention into a flash attention, really requires sort of like an algorithmic trick. Like flash attention is is using sort of a property of mathematics to do an algorithmic transformation of an attention kernel, and for the most part, I don't think compilers, either Helion or Torch Compile, are really able to do that automatically. Torch Compile is able to do that through pattern matching. It's able to like realize like, oh, I see you have an attention there. I'm going to swap in a flash attention for you. I think for Helion, like it makes less sense to do that type of stuff, because really like the reason why people would use Helion as opposed to just Torch Compile directly is because they want to control what the kernel does. And if like we take the thing that the user wrote and we do some sort of like clever rewrite of it, then that's sort of like going away from the like we do what the user tells us to design ethos. Now, like I could see a case where if the user has two different algorithms they want to try, like you can imagine combining them into you can imagine combining them into a single auto tuning run where the auto tuner decides can try them both and switch between them, which I think that makes more sense to add, but not automatic algorithmic transformations.
I think there's one more question from Mitt, which is there a way to pass in FS graph externally and then leverage Helion's auto tuner to get tracking code?
Not currently. You could if you have an FX graph, actually, this would probably work if you pass it as a function. So the way Helion handles function calls is it FX traces them. So if you have an FX graph and you pass it in as a function argument to your Helion kernel and you call it from your Helion kernel, Helion will retrace through it. So as long as you haven't put like non-traceable operations in your graph, then things should work today.
I think Alex asked a question, does Helion compile in Triton? Why not into colors?
So Cutlass isn't really a language. Like I view Cutlass more as like a kernel library. So like Cutlass is sort of like similar to like cuDNN or cuBLAS or something like that. Now there is like a few DSLs that Cutlass exposes, but those are more for like adding epilogues to like the Cutlass matmul. So it's like I think they're not really and they're not really as sort of usable as sort of like a full-fledged DSL. We do use Cutlass in Torch Compile. So Torch Compile will generate Cutlass code, but that's mainly just for like the algorithms in Cutlass, like mainly matmuls.
Great. I think we're almost at time. So I have one last question and then probably that will be end. So I think the two trends seems like on the kernel side is getting more persistent kernel and then mega kernel. I think that's kind of some of the recent kernels have been around this space. And how do you think that changes the language design? For example, persistent kernel means we have different, it's like a workload partitioning as opposed to like tile partition, maybe different way to partition the data. And how do you think about with the mega kernel and then fuse like mega kernel, persistent kernel, how does it change the design of the languages?
Yeah. So Helion's able, as I mentioned sort of earlier, Helion's able to generate persistent kernels automatically because that's mainly like a transformation of sort of how the PIDs are mapped to SMs. I was thinking like I saw some of the recently some of the mega kernel work, and it actually got me sort of thinking about like language ideas of like, okay, like could we use Helion to generate a mega kernel? And so this isn't to be clear, this isn't in the language yet, but like one thing I was thinking about is like we could add something. And so in Helion today you can like do basically like for each style horizontal fusions by having two top level loops. So if you have like an HL.tile loop followed by an HL.tile loop, what will happen is like the first n PIDs will do the first loop, and then the second n plus 1 to n plus m PIDs will do the second loop. I was thinking that like, okay, we could add a new construct to the language like hl.barrier. And if we had a construct of like hl.barrier in the language, then like you could use that same thing to have like additional loops afterwards. And those additional loops could have a data dependency to the prior loops, because like the thing I just described before doesn't work with data dependencies. Like if you have a data dependency between the two loops, like the order of the PIDs isn't guaranteed, so you have a race. But if we had like a barrier construct, what you could do is you could sort of wait for all of the SMs processing the first loop to finish. You could issue a barrier to global memory, and then you could sort of continue on. And by adding basically this like HL barrier concept, you could in theory have like basically define like a mega kernel that does your entire model in just one kernel in Helium. Um, I think that's an exciting idea. I'm still like thinking about like, okay, like is this the right representation? Is this going to deliver performance benefits? How is it going to affect the autotuner? Like, is the autotuner going to be able to, like search over this effectively? But yeah, that's definitely something I've been like thinking about, and if people have other ideas, I'd love to hear them.
Yeah, this is actually very cool point. Yeah, I've been thinking a lot about with all the recent way people writing kernels, since like the languages are now definitely designed with this in mind, especially some of the older style languages. I feel like Helion, the way that the partition data actually may be like at least give the possibility of such that may like have like a persistent kernel or a quote unquote meta kernel be sort of the first class citizen. Uh,
Yeah.
that's very cool. Okay, I think we're at time. Again, I would thanks Jason for the very nice talk. And then yeah, again, I'm a big user for Helion, so I've been wanting to listen to this for fun from yourself. That's very nice.
Thanks again. This is super fun and great questions. I enjoy it.